Greetings. I have been requested to give a lecture of an example of a particular case of rational function in which we will be having a slant and vertical asymptotes. Now, based on the assumption that the students' audience are already familiar with polynomials, they are familiar with the graph of polynomials, they are familiar with interpreting the graph of the polynomials, and also with operation with polynomials, arithmetic operation, in particular division of polynomials, syntactic and long division. Now, as a kind of warm-up and a bit background reminder, I would like to say a few words aside before I go directly to the lecture, to the body of the subject. Now, polynomials, as we already know, are given usually in three forms. One as an algebraic expression, one as an equation, and one as a function. Now, in the form, when they are given in algebraic expression, we know that what the definition of polynomial is. When it is given in the form of in the form of equation, usually the solution is a finite number of values that we replace x with will make the equation true. In case of polynomial as a function, the values that x can assume are almost always is infinitely many. If it is real, infinitely many real numbers. If it is, complex, infinitely many complex values, etc. So this is the way that the polynomials are usually given to us, and we are familiar with the rest. I have written, if you like to write a note of it. Now let me. Now, in a given polynomial, let me take this one out so that we can have the next. Now, in a given polynomial, if we replace the x, let me put that one up because I may need it. Now, in a given polynomial, if we replace the x value of that with a number, we will have what? We will have a finite series of terms, is that right? And each of them are real numbers. So in reality, we are dealing with real numbers. So that means all the properties of real numbers can also apply for polynomials. Now in the set of real numbers, we will have properties like addition, subtraction, multiplication, division, and we have the property of factoring, we have the property of distributive law of multiplication over addition, we have properties of commutativity and associativity. All of them applies in the set of polynomials as well. Now, let me now go to Now, our number system is a base 10 place value system, and we know what that means. Now, if we write, for example, the number I have written here as an example, if we write, let's say, 2,345 in expanded form, we will have written like that. Is that right? This number is what is same as this in expanded form. Now, if we replace the 10 with an x, you see that? We will have a nice looking polynomial. You see that? A polynomial of degree 3. And it does not have to be base 10. It could be any other basis. So in reality, from grade school up, we are dealing with polynomial. And in in grade school that we are working with numbers, in reality, addition, subtraction, and so on, division in particular, we are dealing with polynomials. But we do it not even realizing that and not being told that way, unfortunately, in a sense. Okay, so that about. Now, Suppose that we want to divide 2345, I just made the example, by let's say a number like 13. Now, how do we do that? If we know how to do it because it's a place value, we know the shorthand of that. But if you write it in expanded form and follow the algorithm, exactly same thing we do with polynomials. Exactly same thing. Because the division is a repeated subtraction. So we do this and subtract and we come up with the remainder. All right? So this is another good comparison of polynomials and set of polynomials and set of real numbers. Now, rational functions are, let me just write it you're familiar with. Rational functions are those functions that they are written in the form, in this form. The numerator is a polynomial, denominator is polynomial. Now, I mentioned about rational function, and I did mention about set of real numbers and properties that they have in common. Now, let's see the comparison of rational function with rational numbers, what they have in common, and investigate that one. Now, let me see. Now, in let me see according to the composite number in the set of integers, positive integers, composite number can be decomposed, can be expressed as a product of what? Prime factors. Now, this is called fundamental theorem of what? Of arithmetic that we are familiar with. In contrast, exactly same thing has a term about what? About polynomials. And what is it? It says that every polynomial can be expressed as a product of linear factors. As a product of linear factors in the set of complex and in the set of reals, every polynomial can be written as a what? As a product of linear and or irreducible quadratic factors. You see the similarity, how fantastic they are. They are related. Now, these two terms, the theorem that we know about the fundamental theorem of arithmetic, we know how to decompose a composite number into product of its prime. But in the case of polynomials, he guarantees you can do it, but he doesn't tell you how to do it. And how to do it is another art. And as a matter of fact, long ago, I have uploaded over 1 hour lecture just about the, writing the polynomial into factor form and why they work that way and the way that we can do that. And I do encourage you in my channel to possibly watch that video as well. Okay, now the other things, let's see, I don't have, now the other things that we were talking about rational functions, so let's see other similarities between rational functions and rational numbers. A rational number are those numbers in the form of a over b, where a and b are integers and b of course is not zero. In contrast, the rational functions are those functions in the form of p over x over q of x, where p of x and q of x are what? Are polynomials. And of course we exclude those, we don't exclude, but we treat those factors that they make denominator 0 when we replace x with a number, with a particular number. We treat that one a little differently. Okay, now rational, what other they have in common is that if a rational number is given to us and is not in reduced form, we can go ahead and fundamental theorem of arithmetic give us the permission to go and write it in the product of its prime, and we do it numerator and denominator, and the factors that they have in common we cancel. So we said that the fraction or the rational number is written in the reduced form. And if the numerator is larger than denominator, we usually call it improper fraction. In contrast, we do exactly similar thing with rational functions. So the fundamental term of algebra guarantees that we can factor every given polynomial. So we go ahead, and I already mentioned, there are ways to do it. We try and factor the polynomial into product of its prime, into factors, and then we cancel those factors that they have in common. But again, taken under consideration the one that makes denominator, the value of x that makes denominator 0, we treat that one a little bit differently. Okay, what else is that if a rational number, the numerator is larger than denominator, which means if a is bigger than b, then we call it, I already mentioned, we call it improper fraction. We divide the denominator into numerator and write that rational number into mixed numbers. So I have an example I have written, and exactly same thing we do with polynomials. So I have written an example for you, for those that they like to take notes. Now, 7 divided by 2 is a long division, is equal, the remainder is 1. So we write 7 over 2 in the mixed number form, 3 plus 1/2. Is that right? Exactly same thing we do if we are going to divide x squared plus 3x plus 2 by x minus 3. The quotient will be this and the remainder will be this. So we are writing in the form of this and this. Do you follow me? So we write it that one, and as a matter of fact later we will see that will be the equation of the slant, and we will see why, the reason behind that. Okay, now let me see now. Now I have some hints for you. By the way, I have written that if you want, those of you who like to take notes, I have written this given function, this rational function into this form. Again, I repeat myself, the fundamental term of algebra guarantees we can do such a thing. He doesn't tell you how to do it, but he guarantees. So based on that guarantee, we went ahead and we found that it's easy. Over the integers, we can factor it into these two factors, this given polynomial. Okay, now I have some suggestion to make that they are coming from a very experienced teacher, and I strongly recommend you to follow those. And I'm going to zoom this one for you in case of those that they like to take notes. And I pause for a few seconds because, I wait for a few seconds because you can pause and take a picture or download or write the notes of that. And the hints is that this is a polynomial function and how we start to approach for the sketching the graph of that. Now the procedure that we follow is that first locate all the intercepts, x and y intercepts. We know what x-intercept means. When the y equal to 0, we solve it for that. We find the x-intercept, and we know what the y-intercept is when x is 0, and usually it's easy to determine. Just put for x 0, you find the values of that, of the y-intercept. So first one, that one we do. Then second one, look for the asymptotes. Now we have 3 different kind of asymptotes, or linear asymptotes. We also have curve asymptotes, but that is outside the topic of this subject. Now the linear asymptotes, we will have 3 different kinds. We will have a vertical asymptote, we will have a slant asymptote, and we will have what? We will have a horizontal asymptote. But as already mentioned in the beginning of this lecture, I have been requested to give example that has what? A slant and vertical. So this example applies for that one. Now, then go ahead, and if the degree of numerator is bigger than degree of denominator, as I already mentioned, divide the denominator into numerator and write it in the form of q of x plus remainder over the divisor. All right. Now, whenever the degree of the numerator of the polynomial is 1, 1, 1, more than the degree of the denominator polynomial, we will always have a slant asymptote. You follow me? In this case, that is the case, in fact. The degree of numerator is 2, the degree of denominator is 1, therefore we will expect to have what? A slant asymptote. Okay, then the other thing is very important, I mentioned it again in 2, that I emphasize, and again comes from experienced teacher, and that is, do not let the graphing calculator or computer to replace your thinking. You will be damaging the critical thinking, the analytical thinking, which is mathematics trains you. You will definitely damaging that one if you put your trust always on graphing calculator. Let that to replace your thinking in process. Now, if you want to discuss about the graph of a polynomial or whatever of a function, always try to sketch it without looking at the graphing calculator. Do it on your way, using mathematical work, you're doing what? Planning, think and reflect, and then at the end, look at the graphing calculator to make comparison. This is a very big experienced teacher's advice for you. Now, I'm giving some very good important hint here for sketching the graph of all polynomials in general. In this case, we're discussing and we demonstrate for the polynomials of rational polynomials, is that how to sketch the graph and what kind of hints we can use so that our graph comes much more precise, and also critical thinking is involved. All right. Now, what I do here is that I have written for you. I'm going to zoom it for you and hold it for a few seconds, as I already mentioned. Sketch a mini portion. Sketch a mini portion of the graph at the point of intersection of the graph with the x-axis. I repeat myself, a mini portion of the graph, graph it on the points that the zeros of the polynomial, in a sense. Now, you do the same thing at the vertical asymptote, but you have to know that the function will never hit the graph of the function will never hit the vertical asymptote. The graph of a function may hit the horizontal asymptote or a slant asymptote, but will never ever hit the vertical asymptote. It's natural, because if it hits, that means you have a value of x in that, because the graph is hitting that, and that is, and we know that the vertical asymptote has come at the point that the denominator of the rational fraction for that value of x will be 0. So that is just, again, think and reflect. Now, let's see what I mean by mini graph of that. I demonstrate the idea, and with demonstration a lot easier than to kind of memorize it. So let me zoom it, if I may. Then I wait a few seconds, then I come back. Okay, I'm back. Now, this one, let's now investigate what I mean by mini what, but mini partial of the graph. This one also, I may zoom it for you, is very important, notes here. They are coming from experienced teacher, and please take advantage of that. Now, this is the function was given to me, and I wrote it in that form, in the factor form. Now, behavior of the function in a small neighborhood about what? About -1, 0, which means the 0 of the function. The function hits the x-axis. Now, at that point, we write this given function because we are interested at less than -1, so write it in this form. Write the factor that we want -1, this one separate from these two factors. Do you follow me? Then look what I do. Then my function will be written as a f of x equal to, let this to be g of x. Will be written as a form of f of x equal to g of x times x plus 1. It's just cosmetic work, I haven't done anything. No, because we are interested at the behavior of the function about -1, so determine the g of -1, which will be kind of coefficient of this. So determine that one, and when I put -1 in this, we get what? We get 1 numerator, I get -4 denominator, so I get -1/4. So then write your function approximately will be equal to what? Will be equal to -1/4 of x. You multiply by that, -1/4 of x times -1/4 of 1. So this nice looking linear function comes out of it. You see that? Then we do the very same thing for the second zeros of the function, which is what? At -2. I have done that one, I show you that one also just for the extra practice. And then we are going to put this one in the graph, a mini sketch of the graph, and see how fascinating it helps us for seeing how the function should behave, so that we can see the graph of that ahead of the time in a reality. Okay, in our mind, in fact. Now, the other one is, the second one I have also done. I don't know if you need zooming. Let me zoom in case if you write notes. Okay, now let me go to next one. Another zero of my polynomial, the one that particularly given to me to demonstrate, is when at x equal to -2, which is very similar to the first one, no difference in reality. All right, so what we do, we write the function into in this form. You see, now I wrote the factor x plus 2 next to this one. You see that? I separate them this way purposely. Now, we can let this to be g of x, Then we determine g of -2. Why g of -2? Because we are interested on the behavior of a function about -2 on the x-axis. So I found g of -2, I determine, and this end up to be 1/5. Then I go and distribute 1/5 times x, which is 1/5 of x, and 1/5 times 2, which is 2/5, and go and sketch that one, a mini sketch on the graph that I'm going to show it to you on my graph. I have written that large enough so that I don't really need to zoom in, but you can see it, excuse me. I hope it doesn't fall. Now, look what I did at x -1, as I did the procedure, end up with to be a line. And we know how to sketch the line, We write a slope and the y-intercept. So we determine the y-intercept. We use the definition of a slope to find the second point. And 2 points, 2 distinct points determines a unique line. So we draw a line. That line definitely passes through, definitely will pass through -1, 0. Definitely. Okay, then in that -1, 0, put little slide, you can see that, of the graph. In this case, it's linear. You see that? I put it with the red color. Hopefully it's visible to you. And you do exactly the same thing with -2. Exactly the same thing. So you use that one, this one you use it, and then sketch the linear, and that will pass through that one. Erase the rest of them you don't need. keep a little portion of that. Now look how fantastic is giving you information about what? About he gives you information about the function. Look at that. He says that the function is going to go up and come down. That means has a turning point. You see that? He has a turning point. And he shows also that the function between 0 definitely will not have any other zeros, but you will have a point of concavity, is a concave down. You see, these two are indicating clearly how you could anticipate or how you could see how your function will look like, and also help you for a graph of it when you start to graph it by hand. So this, and then at the point that the denominator is 0, this one is also interesting to investigate. And for this one, look what we will do. We write that one. Where was my function? We write my function. Well, it's mixed up. Now, I write my function in the form of x, what was it, x plus 2, x plus 1 over x, 3, x minus 3. I write x plus 2 times x plus 1 times 1 over x minus 3. So then at x 3, I'm going to find what will be the numerical coefficient of 1 over x minus 3, write it that, and that give me a nice looking hyperbola. And then I draw a little piece of the hyperbola that I can say, hey, the graph should resemble a little bit part of hyperbola for me. That's what, again, I'm anticipating. I'm seeing the picture of that in my head without using calculator. So that is about that one. Now let's go to the graph of that I have done it. Let me go through that, and you can see it for yourself. My apology for not having board to do that. I have very primitive equipment, a cheap camcorder, but as long as I can convey the message to you, I'm happy, and hopefully you are happy. And the point is, the knowledge doesn't matter how you present it. Maybe even this way is better. I hope so. Okay, now let's see. Excuse me. Now this is my graph now. Now I have drawn a slide that I'm going to go through that, but how this one is now to the slant. The slant. I didn't mention it here. Let me go over that. We know that the bond that makes the denominator 0, the value of x, in this case 3, that will be a vertical asymptote. For the slant asymptotes, as I said, you divide the denominator into numerator. First of all, you are expecting, because numerator is 1 degree more than denominator, and then divide denominator into numerator, then you end up with the quotient plus remainder over x minus 3. Then x minus 3, as x goes to infinity, that part of it will be ignored in a sense in the long run, because that is the definition of asymptote. So then we will have an equation of the asymptote that will be y equal x plus 6. I haven't written that one. I don't know why I forgot that part. So this will be the equation of my what? A slant asymptote. You got it, huh? Divide denominator into numerator. The quotient will be the equation of your slant asymptote. Okay, now I go ahead, and this one, now I start to analyze. Now look at that. In these 2 points, I put them with a little bit dark. I don't know if it is visible. As I already explained that one, I'm expecting that the graph to be turning, having a kind of maximum point in here, then coming down because of the definition of the asymptote. So I'm expecting my graph to go down closer and closer to this slant asymptote, and go down this way closer and closer to the vertical asymptote. And I also know the y-intercept, which in this case should be negative, and he hits that one before he goes down. So I have a very good picture how my graph will look like. in my head again, not using calculator. Now the very same is true here. I'm expecting that the graph look like a kind of hyperbola. So I put a little mark here. Is it visible? That part of the hyperbola, because hyperbola looks like this, is that right? So I put a little bit, that's what I'm expecting. Now, when I plug some numbers, 2, 3 for the beginners, I will find that my graph will be, again, coming here, then getting closer and closer to this. So such a graph I'm expecting to have in my head from the knowledge I have is, you know, I'm presenting that as a college algebra level or pre-calculus level. Now, what is this point? That is part of the calculus. With the calculus, taking derivative, we can find out. And also, there is, I brought the subject of calculus, let me say also one word. In calculus, we said differentiability applies continuity, but the converse is not true. But in case of polynomials, the converse is also true. Isn't that fascinating? And it's so good and so easy to work with polynomials when we take the derivative and when we do integration. That is another advantage of knowing polynomial, and polynomial, as already mentioned, I can't emphasize enough how important it is in applied and the pure mathematics, and also in science and engineering, plays very important role. Okay, now for the case of this one, again, I'll go ahead and put numbers. Now, for finding this point, the point that the turning point, that the concavity, this one is kind of concave up. To find that point, we can also use algebraic method. We can use also algebra in case we don't know about calculus, but that is at least 1 hour long lecture. So I'm not going to go through that. But yes, we can find this point algebraically, and we can find this point also algebraically, but through calculus is much easier and faster. You don't have to go through the 1 hour labor to find that one. That's the beauty of calculus. Okay, now I have this one. Oh, by the way, this one I already mentioned it for you. The graph of that, is that right? What do you expect? Now, on the back of that, when I try to sketch this one, I end up to be I try to sketch the graph in a scale. And when I try to make it in a scale, I got kind of out of way. So if we put this one, let's say here, look at that. If I put it here, do you see that hopefully? If I put it here, then this part of it, I already mentioned, we are expecting the graph to go up here, has a turning point to go down this way, and then hit the y-axis and go down this way. So I have a beautiful thing in my head how the graph will look like in this part. And in this part also, I'm expecting to see, I put a little light bar here to look like a hyperbola part of it. So it's going to go down and then get closer and closer to this as the number of x increases. As a matter of fact, if you put a number, now after 3, for example, put 4. You know, immediately in this port, in this intersection of that, y is 6. At this point, y is what? Y is 9, but if you put 4, it goes all the way to, I think, 30. So that means that you go a little bit to the right of 3, you will be dealing with what? With the values of function in this region. So this region of the graph will be what? Will be excluded, and this part, this region of the graph will also be excluded in our discussion. Now, to make it in general, let me also give another one that is kind of, this is not in a scale. That is just we had in our head, I put it in drawing. This is not in a scale. So this is what the graph will be expecting to look like. Then we use graphing calculator to kind of compare to our graph to see we may have done mistake or something. Unfortunately, I don't have a graphing calculator, mine is broken. So I hope and assume, and with the analysis I made, this will be the overall picture. Okay, then I thank you for watching. I wish you all prosperity and good health. And this lecture that I have been requested to demonstrate also motivated me to upload many videos about polynomial from the scratch, from the beginning definition of that to all we need about polynomials. So that means about 30, 40 possibly videos. And hopefully I get the opportunity to do that. And as you have noticed, my method of teaching, I dive deep into the subject. I don't follow recipe, and I don't follow kind of mechanical. You have to know where they come and why they come from. And that is the beauty of mathematics, improves your critical thinking, and that is what mathematics is all about. Okay, then for the second time, I thank you for watching, and I wish you all prosperity and good health, and please stay safe. So long.